Homework 3, Section 1.3, Problem 2. Let f of x equal sine of x cubed minus x cubed. Find the multiplicity of the root r equals 0. So to begin, first define the function f of x as below, and then evaluate various derivatives of f at x equals 0 until we get our final answer at x equals 0. When we do this, we find that the first non-zero derivative is at the ninth derivative. So this is going to be our multiplicity. And so function f has a multiplicity of 9. Part B, locate the root with initial guess x equals 0.1. What are the forward and backward errors of the response? So to begin, invoke fixed point iteration to go ahead and get a numeric answer for the root. And then we know that f has a root at x equals 0, but what numeric value do we get from running fixed point iteration? So to begin fixed point iteration, we're going to use the same code that we used previously. Define a variable a with our initial guess of 0.1. And then this for loop is going to go ahead and evaluate f of a and then set the evaluation equal to a. Run this calculation again several times, printing out the result of a each time, and then evaluate the results. When we do this, we find that after only one iteration, we get pretty darn close to 0, but then after 2 iterations, we get to 0 exactly. And then every iteration afterwards is 0. And so we can go ahead and then evaluate this for the backward error and the forward error shown here. And when we do this, we find that we get a root of 0, a backward error of 1.67 times 10 to the negative 10, and a forward error of 0.1. And so running fixed point iteration a grand total of 15 times yields a final answer of 0. And this comes after we check for precision out to 100 decimal points. And we also are able to evaluate the backward and forward error to a great deal of accuracy. Section 1.4, Problem 3. Apply Newton's method to find the only root to as much accuracy as possible and find the root's multiplicity. Then use modified Newton's method to converge to the root quadratically. Report the forward and backward errors of the best approximation obtained from each method. Part A. Let f of x equal 27x cubed plus 54x squared plus 36x plus 8. Then invoke Newton's method. So to begin, go ahead and define our function f of x, and then define our second function g of x as the first derivative of f with respect to x, and then plot f with respect to x to get a rough idea of where the root lies. In this case, it looks like the root is going to be somewhere between -1 and 0, and so let's go ahead and choose midpoint of 0.5 for our initial guess, and then invoke Newton's method to get a numeric answer. To invoke Newton's method, go ahead and set a equal to -0.5, which is our initial guess, and then we're going to go ahead and run a loop, a grand total of 1,000 times, setting a equal to the result of a minus f of a over g of a, running Newton's method. And then, once we're done running this 1,000 times, we can go ahead and print out the value of a to the console. And then to check our answer, we can go ahead and solve f for 0 to find out where the root lies using the onboard commands within Mathematica. When we do this, we find that the numeric answer from Newton's method yields a result of 0.666, about equal to -2/3, and the onboard solve methods within Mathematica yield a final result of x equals -2/3. And so one thing to note here is that despite running over 1,000 steps of Newton's method, Mathematica is unable to get a more accurate answer out to 7 decimal places, and so we are going to get a little bit of an error here. However, when we invoke the onboard solve functions within Mathematica, we find that the root lies at exactly x equals -2/3. Then we can go ahead and evaluate the backward and forward error for our result. When we do that, we find that the results are 0.125 and 0.166 repeating for the backward and forward errors respectively. And so for Newton's method, the forward backward errors are 0.125 and 1/6 respectively. Modify Newton's method. To begin, start evaluating derivatives of f at x equals -2/3. When we do this, we find that the first non-zero derivative of f at x equals -2/3 is the third derivative, which yields a result of 162. And so the multiplicity is achieved after a grand total of 3 iterations, meaning that our function has a triple root at x equals -2/3. Now we can go ahead and invoke modified Newton's method, which is the formula expressed here. To begin, define the variable a equals negative 0.5, and a second variable, m equals 3. What we can then do is evaluate Newton's method one time, setting a equal to the result of a minus our multiplicity of 3 times the result of f of a over g of a, and then go ahead and evaluate that result down here. When we do this, we find that we get an exact result of negative 2/3. And so, for modified Newton's method, convergence has occurred absolutely to the root after only one step, and our iteration also yielded an exact answer, whereas before, with normal Newton's method, our answer gave out after only a few digits of precision. Problem B. F of x equals 36x to the fourth minus 12x cubed plus 37x squared minus 12x plus 1. Part 1, Newton's method. As before, go ahead and define our function f as below, and also go ahead and define the second function g as the first derivative of f with respect to x, and then plot f from x equals 0 to x equals 1/4 to get a rough idea of where the root lies. When we do this, we find that the root is somewhere between 0 and 0.2, so let's go ahead and set an initial guess of 0.1. Then invoke Newton's method. Here, this is the same code that we had before in order to evaluate a. And while we're at it, go ahead and also evaluate the backward and forward error for our result. Finally, we can solve the function f for 0 with respect to x. When we do this, we get a result of 0.166667 for Newton's method, a result of 0.1616 for the backward error, a result of 0.06 repeating for the forward error, and an absolute answer of x equals 1/6 for the root using the onboard solve methods within Mathematica. And so, Newton's method converges to the solution x equals 1/6 after a grand total of 18 steps within our for loop, and with a backward error and forward error of 0.1616 and 0.066 repeating, respectively. Modified Newton's method. To begin, start evaluating derivatives of f at x equals 1/6. And when we do this, we find that the multiplicity of our function f is 2, meaning that it is a double root. Now we can go ahead and invoke modified Newton's method for a equals 0.1 to begin, multiplicity m equals 2, and then run a grand total of 2 iterations of modified Newton's method, and then our result converges absolutely to the root after only 2 steps. Again, the result is 0.16 repeating. Problem 6. A 10 centimeter high cone contains 60 cubic centimeters of ice cream, including a hemispherical scoop on top. Find the radius of the scoop to 4 correct decimal places. To begin, write out all of the known equations for this ice cream cone, in addition to writing out a variable for our height, which is 10 centimeters. And then once we have all of our known variables, we can go ahead and list our unknown variable r. And once we do this, we can go ahead and define a function f of r for all of the information that we found above equal to this equation here. We can then also take a derivative of f and then invoke Newton's method to solve for the root numerically. Same process as before, go ahead and define a function f. Next, go ahead and plot f to get a rough idea of where the root lies. Go ahead and evaluate f for the first derivative with respect to x. And then down here, we're going to define a third function called h of x, which is going to be defined as f of x over g of x. Next, we can go ahead and invoke Newton's method using the same code that we've seen before and evaluate the equation out for 5 total steps, and then numerically evaluate our result a out to 10 decimal places of precision. And then lastly, we can go ahead and solve f using the onboard solve commands that we've seen before out to 10 decimal places. When we do this, we find that the root lies at 2.020107321, and when we solve this equation using the onboard solve commands within Mathematica, we find that our result exactly matches our result from Newton's method. Therefore, the radius of the scoop is exactly 2.020107321 centimeters.